Hi everyone, welcome to Melissa Math. Today we'll be evaluating the following integral. It's an integral indexed by two arbitrary constants a and b. We're going to be considering integral from minus infinity to infinity of e to the minus ax squared times sine bx squared. Now both of the terms of this integral should look familiar. They are very famous. So we have the Gaussian, of course. We know this integral to be the following. If we integrate e to the minus ax squared over all space, we get square root of pi over alpha, or a, sorry. And if we look at the Fresnel integral, or Fresnel, not really sure how to pronounce it, that integral is the same thing, replacing with a sine ax, and it's actually the square root of pi over 2a. And the integral we have up here is basically a product of the kernels of these integrals, and we would think that it would be interesting as well. I actually found this integral on the R-Math subreddit. There was a post about the most difficult problems you've ever encountered in a math class, and it was given on a take-home exam, open internet, open book. In fact, when you search this integral, you really can't find anything about it. So that's probably why it was given. I've actually never had to use this integral in my studies either, and I haven't found its value in a table of integrals. So if you do, and you have found one, please let me know, because I'm not sure that the final answer is going to be written in the appropriate form. This is just a straightforward generalization of I of 1, which is the integral of e to the minus x squared sine x squared, of course. And this was actually the problem that was given to the student in question. However, if we put in the arbitrary constants, this is something that we would find it in a table of integrals, and it's really not much more work. So we're going to be evaluating IAB and then show that we can reduce it to this form at the end. All right, get started on that. We're going to need a few things to do this. We're not going to need the results of the Fresnel integral or the Fresnel integrals, but we are going to need the Gaussian. So we're going to be using this integral. And we're also going to be using the complex version of the sine. So sine x is 1 over 2i e to the ix minus e to the minus ix. Yep, that's all we need actually. It's pretty straightforward from here. Let's begin. This is equal to integral using the sine formula we just wrote down over 2i e to the I bx squared minus e to the minus I bx squared. This now breaks into two integrals, both of which are easy to do. First integral just has e to the minus. Now we're going to get a Gaussian with a different constant. So we have minus a minus ib here. X squared, of course. And there's another integral as well. There's e to the minus a plus ib. So there's an overall minus sign on that one. And there we go. Now we just apply this formula up here. It's really straightforward. So doing the integral is not the hard part about this problem, but transforming it back to real spaces. So this is just 1 over 2i. Then we have square root of pi over a minus ib. Then we have minus square root of pi over a plus ib. And now we're going to take out the factor of pi and the 2i, writing it as 1 over the square root of a minus ib minus 1 over square root of a plus ib. And now there's basically only one thing we can think of to do, that is to put everything over a common denominator. So we'll do that. Okay, common denominator here is going to be, well, first of all, we're going to multiply this one by square root of a plus ib. We're going to multiply this one by square root of a minus ib. And the product of them both is going to be in the bottom. And we also know that a complex number has a modulus squared equal to z star z, which is exactly what we have down here. So this is just the modulus squared, or we know that the modulus squared of a plus ib squared is a squared plus b squared, just from elementary complex number theory. So you can rewrite this as we have, sorry, there's a square root on this pi. Okay, so now we have square root of pi over 2i. We're going to get the square root of a squared plus b squared coming out. Sorry, that's actually in the bottom. So just to simplify this, we have a square root of pi over square root of a squared plus b squared here. The 1 over 2i stays here. And now we have square root of a plus ib minus square root of a minus ib. So at this point, we can't proceed any further until we decompose it into the polar form. That's pretty straightforward. So for a polar coordinates, we have a plus ib. I'm going to set this equal to r e to the I theta for some theta. This tells us that r squared must be a squared plus b squared, and tangent of the theta must be b over a, which has the following form: square root of a squared plus b squared e to the I inverse tangent b over a. Now we have an a plus or minus ib here, so we'll compute the square root of them at once as follows. Square root of a plus or minus ib is simply the square root of r e to the plus or minus I theta. So now we get the r, which already has a square root in it, so there's going to be a fourth power. So a squared plus b squared to the fourth power. That's an important fourth power. It's going to propagate through the rest of the exercise as well. And we have e to the plus or minus I theta over 2, which we can rewrite as, yeah, we don't even need to keep the theta here. Plus or minus I 1/2 I tangent inverse of b over a. I over 2. Yep, so this is our form for that. Excellent. Now let's plug it in. Square root of pi over a squared plus b squared. 1 over 2i is getting carried around. And the a squared plus b squared to the quarter power can just come out, actually, since it's common to both. Still have the 1 over 2i. And we see that this is just going to have the plus and the minus version in there as well. So e to the I over 2 inverse tangent b over a minus e to the minus I over 2 inverse tangent b over a. Now we can recognize this term as just the sine of this here from our relationship above. This is nothing but. We also want to simplify this. So if we have something to the 1/4 power and something to the 1/2 power, or the square root, just for clarity, then it's just something to the 1/4 minus 1/2, which is 1 minus 2 over 4. So x to the negative 1/4. So basically, there are more powers of x in the bottom, so the quarter goes in the bottom. And this is now square root of pi is all alone. We have a squared plus b squared to the quarter. And now we have the sine of 1/2 inverse tangent b over a. This is our first form of the integral. We can actually do some interesting work with this. For example, we just want to plug in a equals b equals 1 here. If we do this, then we have I of 1, 1 equal to square root of pi over 1 plus 1 is 2, so 2 to the quarter. And now we have sine of this. So inverse tangent of 1, which is what b over a is equal to pi over 4, since pi over 4 is the angle that has a tangent of 1. So this becomes a sine of pi over 8. And that's a good enough form if you just want this integral. This is actually less than the square root of pi. So by putting in the extra sine x squared term, we actually decrease the value of the integral. And in fact, it's have some exact values here. It's on this one. Yeah. It is approximately 0.32 square roots of pi, which is about 0.57 if you wanted to know. And we just computed this integral, this one here. This integral is equal to this value here, but that's just a check. So I had previously computed this value, and I just wanted to make sure that if I put the a and the b in, it got the same value. That's great. So that's actually not what we want, though. So anytime we see, if we have a trig function of an inverse trig function, we want to simplify that because we know it should be possible somehow. So now we want to begin that process. This is actually the trickiest part of the integral. If you notice, the actual integration was trivial, just a consequence of the Gaussian integral formula. But we spent a lot of time with the complex numbers in the Cartesian and the polar form, so we could get it back to the real situation, since it is in fact a real integral. That's what happens when you transform to the complex plane. It becomes easier to do what you want to do, but harder to get back to where you started or where you want to go. Okay. So we want to use some trig identities to help us with this. In particular, so we showed that this integral is actually, we don't need this anymore. So we've already showed that this integral can be written in the following form. We had the square roots of pi, and then we had a squared plus b squared to the quarter power in the denominator, and we had the sine of 1/2 inverse tangent of b over a. That's what we had so far. We want to get rid of this trig function, and if we just had sine of tangent b over a, it will be easy since we know how to draw the right triangle for that and everything. But to get it into that form, it's not very difficult. We'll just be using this identity. So I always recall this one from quantum mechanics since we have the sine squared integrals all the time. So this identity states that sine squared of x is equal to 1 minus cos 2x over 2, which we can then rewrite in this form. We're going to let x go to x over 2 and take the square root of both sides. So sine of x over 2 is nothing but square root of 1 minus cosine x over 2. We're going to need this. And yep, this is how we can get back to where we want to go. We're going to do this as follows. Slight abuse of notation here. I'm going to define a different x. So let x be b over a. So if we do that, and we're going to let phi be equal to not 1/2 tangent, but just tangent b over a, or tangent phi is equal to x. We just put the x here. So then we're going to be simplifying sine of 1/2 inverse tangent b over a is sine of 1/2 inverse tangent of x, which we just defined. And we're going to use this formula here. Yeah, tan phi is equal to x. So we have phi over 2 here. There we go. I guess I can keep the additional step just for clarity. Sine of phi over 2. Now we're going to use this formula with phi plugged in. This is just the square root of 1 minus cosine phi over 2. So now all we have to do is draw the right triangle like we always do for this sort of thing. So we have a triangle like this with an angle phi, and we know that tan phi is equal to x, so we put an x here and a 1 here. This becomes 1 plus x squared, and we're good to go. This actually tells us that cosine of phi is just 1 over, so it's the adjacent over the hypotenuse, 1 over 1 plus x squared in the square root. Okay, so now we have sine phi over 2 is equal to, I'm going to factor out the square root of 2 since it's going to get messy. 1 over square root of 2. And now we have 1 minus 1 over the square root of 1 plus x squared. So that's what the triangle tells us, but this looks pretty bad. We do not like how this looks at all. In fact, we have to simplify it by putting x to be b over a, but you can see how if we have to use this formula at all, it gets pretty messy. 1 over square root of 2, square root of 1 minus 1 over c, just so, it's so messy. 1 plus b squared over a squared. Now we're going to simplify this as follows. 1 minus 1 over square root. Okay, so we're going to factor out the a squared here. 1 over a squared rather. So this becomes a squared plus b squared. Since we already have a squared plus b squared in the formula, we would like to just keep everything in terms of that. So now we can turn this into a regular a, put it on top of that, and we're pretty much done. This becomes 1 over the square root of 2, square root of 1 minus a over square root of a squared plus b squared. Now we can finally celebrate by writing our integral down. I of a and b is now equal to, we have, I'm going to combine this square root of 2 with the pi, just for notational clarity. Square root of pi over 2 over a squared plus b squared to the quarter is still there. And our new term, which we spent a lot of time with, is now 1 minus a over square root of a squared plus b squared. All right, let's talk about for which a and b this is valid. So currently it only works for a and b greater than 0. A certainly has to be positive. Actually, I guess they can be, yeah. We can let a be 0, but we don't really care about that case since it's trivial. It does work for a equals 0. A has to be at least greater than or equal to 0 because we do not want terms like this. We just don't want that because that's certainly not going to converge. It's going to grow far faster than the oscillating sine function. And b has to be positive right now, but we'll extend it now to show you how we can include negative b as well. Okay. It's actually just a simple consequence of the parity of the sine and the arctan function. And if we saw this in a table of values of integrals, it would certainly tell you for which values of the constants it works for, so that's an important part of the process as well. Okay, so now we're going to use the fact that sine and inverse tangent are odd. And that should be pretty much it. Yeah, so we're just going to note here that sine of inverse tangent of minus x is just equal to sine of minus inverse tangent of x. Since the inverse tangent is odd, it just puts the minus sign outside. And now we can put the minus sign outside there as well. And now we're going to use this, go back to our first formulation to look at the b arbitrary situation. So now we're going to let b goes to a minus b for b greater than 0. So I of a and minus b is now equal to square root of pi over a squared plus b squared 1/4. Doing what we just did up here, sine 1/2 inverse tangent of minus b over a, which we can simplify by just taking the minus sign, putting it out here, since we already did the work for that. Minus square root of pi over a squared plus b squared to the quarter. Sine 1/2 inverse tangent b over a, which is just minus I of a and minus b. So yeah, that sounds fantastic. We can write our formula in a slightly different way now. We can now generalize it, write down the conditions here. We have a greater than equal to 0 and b plus or minus b. We want to let b be arbitrary. It just puts a plus or minus here. No problem. Okay, this is my solution to the integral. And like I said, if you do stumble upon this integral in a table and it's written somewhere much better than this, please let me know, because this is quite ugly. I have never used it in my studies before, and I haven't found a solution online, because when you search it on Google, by design of the professor, you get like 3 results, and none of them are in any way related to this. So yeah, if you know anything about it, please let me know, and I'll definitely do some more integrals in the future. So feel free to subscribe, and have a great day.